In this video, we're going to take a close look at the reaction of halogens, chlorine and bromine, under the influence of light with hydrocarbons. Start off with a really simple reaction where we take cyclohexane and chlorine with light. Cyclohexane is simple because all the hydrogens are the same, so we don't have to worry about selectivity. So what's the mechanism? Well, the start is really simple. You initiate the reaction by shining light on the chlorine, getting two chlorine atom radicals. Propagation, how's that going to work? Well, here's two possible mechanisms. In both, the first case, they're both the same. So the chlorine radical that we reduce extracts a hydrogen and gives a cyclohexyl radical. That's up here, that's down here. But in A, we make a difference by saying that cyclohexyl radical reacts with a chlorine molecule, extracts a chlorine radical from it, and gives you the product. Or we could simply take the cyclohexyl radical, react it with the second chlorine radical we did in the initiation step, and form our product. Both of these mechanisms give us our product. Which one's correct? They both would work in principle. Well, the key thing is this is a chain reaction. The B is a stoichiometric reaction. We use both chlorine radicals in the initial reaction. There's nothing to continue. So the only way to continue B would be take a new chlorine molecule, hit it with light again. That's not a chain reaction. But A is a chain reaction because when we react the cyclohexyl radical here with a chlorine molecule, we reproduce a new chlorine radical which can come up and do the reaction in step 1 again. So A is indeed the correct reaction. These are the propagation steps of the reaction. So we have initiation, we have propagation, and then of course we need termination. Termination is simply getting any two radicals together which don't continue the chain. So if we did that chlorine radical with cyclohexyl radical, we get one more molar product, one more molecule product, but it wouldn't lead further in the chain. Two chlorine radicals could just unite and go back to the chlorine molecule. That wouldn't be useful either. There's any combination of radicals which doesn't lead to the chain is a termination step. So that was interesting, but all the hydrogens are the same. What if they're not all the same? So let's do a simple case. Propane. So we have methyls and we have this methylene, and therefore we get two possible products. So what relative yields would you expect if all the CH bonds were equally likely to react? How can we figure this out? Well, here's some possible answers. Well, how many hydrogens are there? Well, there are 8. There's 6 in the methyls, 2 in the middle, 8 total. Well, if we do it purely statistical, the 2 in the middle would be 2 out of 8, or 25%. So the answer here would be C. Purely statistical, we'd expect a 25% yield of the 2 substituted propane and a 75% yield of the 1 substituted propane. What do we actually get? What do we get? We get 55-45. In fact, so what we see is the 2 substituted is not 25%. In fact, it's majority. It's 55%. So there must be some inherent reason why the CH bonds in the middle are more reactive. And we can see this even more clearly if we go look to the case where we have a tertiary carbon. Here in this isobutane, we have only 1 hydrogen out of 10 is on that central hydrogen, or central carbon, but it produces 37% of the yield. So obviously, again, there must be some selectivity for that central atom. Now here, the methyls actually win, but of course there are 9 of them. So it's quite clear that there's something favored for that central atom. Now, how do we explain this? Well, of course, what we do is we explain it with bond energies. If we look at the bond energies, a primary bond, 423 kilojoules per mole, that's how much energy it takes to break it, is considerably stronger than a tertiary with 397. If we compare that to 431, we can actually calculate out energies for the overall reaction. So primary would be only minus 8 kilojoules per mole, whereas tertiary is minus 34, a much more exothermic reaction. Now, primary to tertiary, what is the difference? Well, the difference is 26 kilojoules per mole. So in other words, the isobutane here, that central CH is preferred because the thermodynamic product here is just considerably more stable. Well, the radical, not the actual, this is the energy of the radical underneath. So we're looking at the intermediate, but the intermediate that leads to the tertiary one being substituted is 26 kilojoules per mole more stable than the intermediate which leads to the primary. That's a lot of energy. So we can correct for frequency. So if we had this is showing you how much more reactive they are in terms of ratios. So up here we have to get 55% of the secondary one, but there's 2 positions, 45% of the methyls positions, there's 6 of those. So we divide 55 by 2, 45 by 2. It says that the secondary is 3.7 times more reactive than the primary. Do the same calculation for the tertiary one. This 37% is over only 1 hydrogen. The 63% is over 9. So if you figure out these ratios, 37 over 1 over 63 over 9, it's 5.3. So it says a secondary hydrogen is 3.7 times more reactive than a primary. Tertiary is 5.3 times more reactive than a primary. That's a lot of math, but that's how the numbers work out. Now, if they were in equilibrium, okay, you have to remember this. If the radicals, when I say they, I mean the radicals were in equilibrium. The radicals in equilibrium, you have to remember this magic number here of 5.7. Is that 5.7 is a order of magnitude in an equilibrium constant. 5.7 kilojoules is an order of magnitude on an equilibrium constant. This is actually discussed in the book, and I'm not sure if you discussed it in 331 or not, but it's a very useful number to do. So to calculate the equilibrium constant for between the radical differences, you take 26 divided by 5.7. 10 to that number is 36,000. So if they're in equilibrium, it would be 36,000. So even though there's a lot that tertiary is favored, it's certainly this 36,000 is a huge difference. We're nowhere near equilibrium. So let's see how this works. So here's actually the data for chlorine. So we're going to pull off the tertiary hydrogen, and we're going to go to the tertiary radical in the green line here, or the top line. We're going to pull off a methyl hydrogen, and we'll go to the methyl radical. So these are the radicals, not the final products. And this is where we know what that energy difference is. It's an exothermic reaction, and we know that the tertiary one gives you 26 kilojoules per mole more favorable than the primary. Nothing's to scale here, by the way. This energy difference here is 2600. Well, the key thing is this is not what determines the relative rates. What determines the relative rates is the difference in energy between the transition states up on top. Now, that gave us a rate. We from our relative amounts, we did our calculation on the previous page that the tertiary was 5.3 times more reactive than the primary, purely by our observed yields. Now, if we work backwards and we say, well, that's our equilibrium constant, what difference in delta G's up here? We're assuming. I mean, I've been saying delta H's, but we're basically neglecting entropy, so we're calling this delta G, so we can do equilibrium constants. So this up here is what's called delta G, or delta G double dagger. It's often written, and this is the difference between the transition state energies, and we can calculate out based on this magic equation that the difference up here is 4.1 kilojoules per mole. So what this says is that down here they spread out by minus 26. Up here, the transition state that leads to the higher product is only 4.1 kilojoules split from the one that leads to the more tertiary product. Why is that? Well, because they still look more like the product. The hydrogens are only starting to stretch. They look more like they look more like the initial reactant. I said it backwards. They look more like the initial reactant because the reaction is just starting up here, so they haven't had all that much time to spread out yet. Okay, that's the story for chlorine. Okay, so the transition state difference is only about 16% of the product difference. I simply saying 4.1 over 26, and so that is our first case. Now we're going to go to bromine. When you do the same reaction of bromine, it turns out that almost all the bromine goes tertiary. It's better than 99%. Less than 1% goes to the methyl. In other words, when they say less than 1%, they probably couldn't measure it. So anyway, we can begin to do our same calculation. 99% divided by 1, less than 1 divided by 90, gives us a number which is greater than 890. But again, if they were in equilibrium, it's still 36,000. Well, 890 is still a long way from 36,000, but let's look at the chart again. Well, in the case of bromine, HBr is not nearly as stable as a molecule as is HCl. So this is actually an endothermic reaction. It's uphill. It's uphill to form this radical. And being uphill, it changes everything, because now the transition states are closer to the product than they were to the reactant. In the case of chlorine, it was an exothermic reaction, so these guys are down here, and the transition state looked more like the reactant. We can do the same calculation based upon the ratio that we calculated of 890. We can figure out that delta G has to be minus 17. So now this number is minus 17 versus 26, and it's a 65%. 65% of the product difference is now in the transition state. So these two reactions are very, very different. Is that when the reaction was exothermic, the transition states looked mostly like the reactants, but the reactant was identical, so there wasn't much splitting. When it's endothermic, the transition states look more like the product. There's a big energy difference between the product, so there's a big energy difference between the transition states. And this is basically what's responsible for the selectivity, because now, since there's a big energy difference here, it's much more likely to go over the lower hump than over the top hump. So to summarize, radical formation by chlorination is exothermic and not very selective. Only 5.3 tertiary versus primary. Delta G dagger is a lot smaller than delta G 0. So this is transition state. This is the product ratio. Radical formation by bromination is endothermic and is very selective, 890 to 1. And the delta G dagger is only a little bit smaller. So the transition state splitting is only a little bit smaller than the product splitting. So this is really kind of interesting. Now, this is the basis for what's known as the Hammond postulate. This is taken out of the book. There's a lot to read. Read it for you. The Hammond postulate gives information about the structure of transition states. It says that two states that interconvert directly are directly linked in a reaction profile diagram, and that are close in energy are also similar in structure. So a transition state will be more like the starting material, an intermediate or the product it is close in energy to, if it is in close in energy to one of these observable structures. So it simply says energetically, the transition state, transition state is more similar in structure to either the reactant or the product, depending on whether it's endothermic or exothermic. So in an exothermic reaction, this means you're going downhill. That means the top of the hill will look more like reactants. If it's endothermic, it'll look more like products, because now it's going up the hill, and so the products are the top one up there. If the transition state looks more like products, then it's more selective, because the products have a different structure. The transition states will have a significantly different structure. Now, this is, in the ideal case, and this halogenation is probably the best case of the Hammond postulate that you run into in simple chemistry. But the basic idea applies in any reaction, and it sounds a little bit complicated, and it is. But if you think about it a little bit, it's not too bad. So let's just look at it again. This is chlorination. There's only a small difference in transition state energies. It's only 4 kilojoules different. So it's not very selective reaction. In other words, it doesn't make that much difference which transition state you take going over here. And of course, that means that you get a lot of them going the wrong way. A lot of them go to the primary case. Whereas here in the endothermic case with bromination, it's much more difficult to go over the top one, so they're much more selective because most all molecules want to follow the lower route. And so the net result of this is that the reaction of a hydrocarbon of chlorine is not very useful at all because there's no selectivity. With bromine, there is a selectivity, and the bromine will seek out those tertiary centers or other stable centers as well, such as benzylic centers or allylic centers. Anything which gives you a nice stable radical, bromination will actually work on, whereas chlorination never works very well. You could ask about the other halogens. Well, iodine distillate doesn't react. It's not reactive enough. Fluorine reacts with everything, and fluorine is too reactive because things can explode. There's no selectivity at all. Everything just goes to hell with fluorine. So bromine useful, chlorine not so useful. Fluorine stay away from. You can blow yourself up or something. Iodine doesn't react. So that's the story, and I hope you enjoyed that clever tale.